so what's an invariant subspace? I'll start with the definition. Definition is that for a linear operator on V, so I said if a linear map is from V to V so that the domain and the target spaces are the same, then we call such a linear map as an operator. So we discussed this a few lectures ago. If there's a subspace U in V satisfies T of U is included in U, okay? Then we say, we call U an invariant subspace of V under T, or with respect to T, okay? And that's an important one because then you can restrict the operator T to just this subspace, and I'll define that restriction a little later. Okay, so some examples. The simplest one is just 0. Now, T of 0 is 0, so this space is just going to be itself, right? So this is going to be true, rather trivially. And then another one would be V itself, because by definition, T of V will be a subset of V because it's an operator on V. So anything apply, any vector, if you apply T, it's still in V because it's an operator. Slightly less trivial examples are, say, null of T. So this one, let's think about this. What is T of null of T? Well, anything in the null of T, if you apply T to it, you get what? 0. So what will be this resulting set? It'll just be 0, right? But then 0 is a subset of any other subspace, right? Because any subspace should have a 0 there, so this is a subset of null T as well. Okay, so that's still true. And then you have range of T, and by definition, T of V is equal to range of T, right? So range of T means you take all the vectors in your domain, apply T to it, and collect them. That ends up being a subspace of the target vector space, right? But because range of T is now a subspace of V, if you now, so if you take this range of T, subspace of V, and you apply T both sides, then T of range of T will be a subset of T of V, just because this is a subset of V. Range of T is a subset of V, so if you apply T, the inclusion still holds, right? But then, as I just said above, this is same as range of T, so that's true, okay? But there are many many others depending on the t. So if we work with some more concrete t, we can find more. Right? Now, 5.5 and 5.7 defines what you've been seeing a lot in the previous linear algebra course, which are the eigenvalues and eigenvectors. And this is really at the core of this book. So if you look at the preface of the Exler's book, Linear Algebra Done Right, it says that a lot of the linear algebra is taught wrong because whenever they discuss eigenvalues, they define eigenvalues as like a determinant of a minus lambda I equals to 0, right? That's how we do this, and then you learn determinant in the beginning of the lecture, and then you just use it without really thinking about what it means. And this entire book tries to stick to the original idea of an eigenvector and eigenvalue by giving the following definition. So, for T, a linear operator on V, if V in V, V not equals to 0, satisfies T of V equals to lambda of V, then lambda is called an eigenvalue, and V is called an eigenvector of T. Okay, so that's the definition. In other words, it's a special kind of vector where if you apply T, it acts as just some scalar multiplication. Okay? Another way to say this is to say that if you think about the one-dimensional subspace spanned by V, okay, then if you apply T, that gives you lambda V, which is again just some multiple of V. So if you span with this guy, you still get the same subspace. You could have lambda as 0. The definition does not allow V to be 0, but lambda could still be 0. So you might either get a 0-dimensional space if lambda is 0, or you might get a 1-dimensional space, subspace. But either way, it means that the 1-dimensional subspace generated by the span of V is invariant under this T. That's what it means. Okay? So that's how these two concepts are related. Right? Right? So please think of eigenvalues, eigenvectors that way. And maybe, we should start with proving something almost immediate from our previous discussion. So 5.6 says the following are equivalent, and A, lambda is an eigenvalue of T. B, T minus lambda I is not injective. Okay, and C, T minus lambda I is not surjective. And then D, T minus lambda I is not invertible. Okay, so these four statements are equivalent. And this has to do with one of the theorems that we solved before, we proved before. Here, this I is the identity operator on V, okay? And this follows from 3.69, if you recall, in 3.69, in a finite dimensional vector space, oh, I should say V is finite dimensional, okay? So for finite dimensional, for V finite dimensional, it says T is injective, B, T is surjective, and C, T is invertible. These three are equivalent for finite dimensional spaces. If T is an operator on V, then these three are equivalent. That's what we proved in 3.69. So if you apply it here, B, C, D are equivalent. If I replace T by T minus lambda I, and then, you know, these statements are P if and only if Q, but if this is true, then not Q is if and only if P, just by taking the contrapositivist. So with the not, these three will still be equal. So if this is an if and only if with any one of these, then all of this will be equivalent. All right. So let's think about that. And if you look at this right here, see TV equals to lambda V, that means TV minus lambda times IV. I can stick an I there because I doesn't do anything. IV is same as V, right? I moved it to the left side, and then if I rewrite this, I get T minus lambda I V equals to 0 with V non-zero. So what does that? That means the null space of this is non-zero, right? There's a non-zero vector, so the null space is non-trivial. If you have a non-trivial null space, what does that mean? It's not injective. That's what we learned way before, right? So A implies B. Right? Also, B implies A as well, because you can start from here. If it's not injective, then such a V exists, and then if you go this way, then you see that means lambda is an eigenvalue. So this simple calculation shows that A and B are equivalent, and 3.69 implies B, C, D are equivalent. Okay, so from now on, whenever we want to show that lambda is an eigenvalue, we can use any one of these criteria. We can show that T minus lambda is not injective, or we can show that T minus lambda is lacking some output, or it's not invertible. Okay, so that's what I want to say. Okay, so let's think of a more specific example here. Here we have a linear operator on F2, and it's a map that sends W comma Z to negative Z comma W. So in case of R2, you can think of X and Y. So X comma Y is sent to negative Y comma X. Now, the reason I like this example is because this example demonstrates that depending on what ground field or base field you use, sometimes your eigenvalue may not exist and sometimes it might exist. Okay, so case when F is just a set of real numbers. Okay, now in this case, see, it's customary to use X and Y for real numbers and then Z for complex numbers, Z and W for complex numbers, so that's why I'm writing it like that. But in terms of x and y are real, you can think of this as on R2. So x and y. Suppose you have 2, 1. Okay, so where does 2, 1 get sent to? 2, 1 gets sent to?
-1, 2.
Yeah, -1, 2, right? Now where's that at? -1, 2. So this went here. Okay? Let's pick another one. What about -2, 0? Where does that get sent to? This point here. -0, -2, right? Which is 0, -2. Right? Where's that? So that gets sent here. Okay. So what does this map do? Yeah, it's a rotation by 90 degrees, right? Counterclockwise. Yeah. So you may recognize this one in high school algebra course or somewhere that this is called one of the transformations, right? So this one was rotation by 90 degrees. And what that means is that since rotation does not fix any direction, the above t does not have any eigenvalues. Okay, so the only thing that gets fixed under t is just 0 itself. Okay, t does not have any eigenvalues. On the other hand, if you have case the base field is equal to c, then let's just write down what it means. So if lambda is an eigenvalue, we want to say that twz is equal to lambda times wz, but by definition we have negative z comma w equal to lambda times wz, right? And that means I have negative z equals to lambda w and w is equal to lambda z. Well, let's just take this one and plug it into here. And that gives us that negative z equals to lambda squared times z. And if I move this to the other side, you get lambda squared plus 1 times z equal to 0. So either z is 0 or lambda squared plus 1 is 0, but z, if I set z as 0, then w will be forced to be 0 as well, right? If z is 0 and w will be 0, so you get 0, 0 as the vector, but that won't be an eigenvector. Eigenvectors are never allowed to be the 0 vector, so z can't be 0. If you're looking for an eigenvector, z can't be 0, so lambda squared plus 1 has to be 0. Now at first you might say, oh, that's impossible, but look, we're working on c, right? So we're allowing complex number solutions. So what is that? Lambda squared is -1, so lambda is plus or minus I. Yeah, plus minus square root of -1, that's what you get, but that's I, right? So we can think about those two cases. When lambda is I, then you have, so when lambda is I, we have w equal to I times z, so that I can take wz to be I times 1. If I just take z as 1, that's one eigenvector. Okay? And then if I take lambda as negative I, then because again w is equal to iz, I can take wz as negative I comma 1. Okay? And these are both eigenvectors. These are both eigenvectors for eigenvalues I and negative I. Now, although this goes against the book's philosophy, let's just try to cheat a little bit and see what this would have been in the context of your calculation-based linear algebra. So how did we do that? Well, first notice that if I have x comma or w comma z, and if I have this times this gives you negative. So if I have 0, negative 1, which is negative z here, and then if I have 1, 0, would be w. This one would be exactly this one, right? So if I take the matrix of T under the standard basis F2, F2 has a standard basis, right? Not all vector spaces have standard basis, but this one does have it. It's 1, 0 and 0, 1. So M under those standard basis is this matrix 0, negative 1, 1, 0. And if we do the subtract off the lambda off from the diagonal thingy and take the determinant equal to 0, that does give us lambda squared plus 1 equal to 0 because it's AD minus BC, so that's what you get. So that you get lambda as plus minus I, and when you have A lambda is I, then you have negative I, negative 1, 1, positive I, A, B equal to 0, 0. That's what you solve for getting the eigenvector, right? And you have many choices, but if I just choose B to be 1, I mean, A to be 1 is another choice, but I just want to be consistent with this one. So I'm going to choose B as 1. Then the top line says negative IA minus 1B equal to 0, so that negative IA is negative 1 times 1, and you move it to the other side, you get this, so that A is equal to 1 divided by negative I. And if you rationalize the denominator by multiplying I top and bottom, I squared is negative 1, so negative, negative 1, that's just 1, right? And you just get I. So you do get A comma B as I and 1, which is exactly the same as this one, okay? And then you can also choose lambda equals a negative I, and you choose B as 1, you'll see that you get this other vector, okay? So what we are doing is exactly the same, and of course, this makes the entire process of finding eigenvalues and eigenvectors very algorithmic, whereas here, it doesn't seem like we're following an algorithm, we're just following the definitions and see what we can do every time, right? But this is the way the book forces us to think, because by doing this, you get a more conceptual understanding of what's going on. Whereas if you do this, you might be able to compute things, but have no understanding at all of what's going on, okay? So I hope you kind of see how these two things are related. Okay, this next theorem simply says that if you have a list of eigenvectors that have all distinct eigenvalues, then they must be linearly independent. So let's see how that works. So suppose C1, V1, Cn, Vn is equal to 0. Then, if we apply t, then you get t of C1, V1, Cn, Vn is also t of 0, but if you have a linear map, 0 always goes to 0, so that's what you get. And therefore, if we have t C1 t of V1 plus Cn t of Vn equal to 0. But then these are all eigenvectors with eigenvalues lambda 1 through lambda n, so you get C1 lambda 1 V1 Cn lambda n Vn equals to 0. Okay? So now what do we do? Well, I guess I should have started with the induction, but let's just say, so this is true for all cases. Okay? So we prove by induction, with the base case. If you have a single non-zero vector, it's always linearly independent, right? So n equals to 1, trivially true. So let's just say that suppose V1 through Vn minus 1 is linearly independent whenever the eigenvalues are distinct. Okay. So let's say you've proved that until n minus 1, length n minus 1 list, if you have distinct eigenvalues, then we always know that it's linearly independent. Okay. So in that case, what we do is we take this thing and multiply this by lambda n. Okay. So we have C1 lambda n V1 plus Cn lambda n Vn equals to 0. Maybe this indices are not so clear, so let me write a few more terms. Okay, so C2 lambda n V2, so it's always lambda n, right? Until you reach Cn lambda n Vn equals to 0. But then we also have this guy, right? So from here, we write down C1 lambda 1 V1 plus C2 lambda 2 V2 plus Cn lambda n Vn equals to 0. Okay? And then you subtract. If you subtract, then you get C1 lambda n minus lambda 1 V1 plus C2 lambda n minus lambda 2 V2 plus Cn minus 1, because this last one gets cancelled away, the one right before will be Cn minus 1, right? So it'll be lambda n minus 1 Vn minus 1 equals to 0. And this is a scalar, this is a scalar, this is a scalar, right? And because we know that v1, v2 until vn minus 1 is linearly independent, because it's a length n minus 1, what do we know about these? These must be zeros, okay? But we also know that lambda n is distinct from all of lambda 1 through lambda n minus 1. So these are never 0. So if these are not 0, then what has to be 0? C1 has to be 0, C2 has to be 0, all the way up till Cn minus 1 has to be 0. Okay? But once you have that, then when you plug in these values back in here, we see that 0 v1 plus 0 v2 plus 0 vn minus 1 plus cn vn minus vn is also 0, right? Just by taking these and plugging it back in here. But since these are 0, you have a non-zero vector times some scalar equal to 0, so that cn has to be 0 as well. Okay? And because we've showed all the coefficients are 0, starting with this, the induction shows that this is true. Okay. All right. So let me just say Cn is 0. So QED proof is done, and I just want to write down a quick corollary, which is 5.13. Any t on an operator, any t an operator on a finite dimensional vector space V can have at most dimension V distinct eigenvalues. Okay. Because if it had more, then our previous theorem would be applied, and you have a linearly independent list that has length greater than dimension V, and that's a no-no, right? So we always we've learned a few lectures ago that a spanning list is always bigger or equal length than a linearly independent list, right? Dimension V means there's a spanning list of this size. Therefore, a linearly independent list must have this or less length. Okay? So that's the maximum number of distinct eigenvalues. Okay, so what we plan to do in the following lectures is to take any operator and try to describe that from the building blocks of that operator. So you want to start with an operator and look at what the operator does in some of the smaller subspaces. And that's when we start talking about restriction and quotient operators. So suppose T is an operator on V, and U is an invariant subspace. Okay. i.e., U is an invariant subspace. Then a T of T restricted to U is a map from U to U, so it's an operator on U, such that anything that's in this subspace is sent to T of U. This makes sense because any element in U, any vector in U is by definition a vector in V, right? But then because T of U is inside U, if you just take T of U, this will belong to U. Okay, so this restriction makes sense. And notice that this restriction will only make sense if it's an invariant subspace. If this is not true, then it wouldn't work. Okay? Okay, and then secondly, there's a T. Unfortunately, these two look very similar. One is straight down and the other is slanted. So T quotient by U is a map from the quotient space to the quotient space. We talked about this quotient space in the previous lecture, right? And it sends, what are elements in here? This is V plus U. That's what the elements in here look like, right? And then you send this to T of V plus U. Okay. Since T of V always belong to V, so you have a vector in V plus U, so this is definitely an element in V. Okay. Now, the immediate question is, suppose you have some well-behaved subspace U, and you know these two fully. Does that tell us what T is? Like that's hopefully, if that's true, then this kind of idea can fully describe T. But this following example shows you that it's not that simple. So let me give you this example, which is 5.15. You define T, X, Y as Y comma 0. Okay. So T is a linear operator on F2. Okay. So you have either two real numbers or two complex numbers. So and that space is sent to this. Okay. Now you have you define U as space of X comma 0. X in F. But if you think about it, this is really the null space of T. Right? So if you take X comma 0 and send it via this, you get 0 comma 0. So that's the null space. Okay? So if I define U as the null space of T, which is this, then immediately what you see is that T restricted to U. Oh, by the way, in the very beginning of today's lecture, we talked about the fact that null space is always an invariant subspace, right? So for any operator T, the zero space, the entire space V, the null space, and range of T, those are 4 examples. Some of them might be the same. Some you might have a surjective map so that the range of T is same as the entire V. You might have an injective operator so that the null space is exactly same as the trivial subspace. But this is one-dimensional. So in this case, null space is not a trivial example. And we do know that this is a invariant subspace, which allows us to take the restriction. Okay. Now, but what is T restricted to U? On this space, what does T do? So if I take anything in U, T of U would be, what is U again?
Null T.
Null space. So if you take anything in the null space, T of U would be?
0.
0. So this restriction is just completely 0. Okay. Another thing that you observe is that there does not exist an invariant subspace W such that F2 is same as U plus W. Okay. I mean, this is in a sense what we want to do in the future. We'll see later that for some specific types of operators, you can actually do such a thing. You can build the entire thing as out of invariant subspaces, and that in turn, wait till at the end of this lecture, it shows the Jordan normal form. Okay. So this is the kind of goal that we want, but for this specific example, this actually doesn't work. And in the context of matrices, if you write the matrix for this one, this is really what? It's 0, 1, 0, 0, right? That's what this is the matrix for that one, right? And such a matrix is called the nilpotent matrix because if you square it, it's 0. And other examples of nilpotent are like 0, 0, 0 everywhere, but then 1, 1, and then 0. This in dimension 3, you have a nilpotent something like this. These are the bad guys. These are the ones that make it hard to decompose into one-dimensional subspaces. And if none of these existed, then we would have a full diagonalization. But because of these, there's some limits to. There's some cases you can't divide them into further smaller subspaces, and then you end up with something called the Jordan normal form. Okay. All right. So coming back, how do I prove this? Well, first of all, what's the dimension of this guy? 2. Just think of R2 or C2. 2. And we already know that this is dimension 1 because this is x times 1 comma 0, so this is a span of 1 comma 0. Right? So it's dimension 1. And for direct sum, we proved that dimension of the entire thing is dimension of each one of them added, right? So we proved that. So this must be dimension 1. Now if this is dimension 1, then it's span of one vector, which also happens to be an eigenvector of this guy. Agreed? Right, so that was our definition of an eigenvector, right? So if such one-dimensional invariant W existed, then W would be span of some vector small w here, where so because it's one-dimensional, W cannot be a 0 vector because span of a 0 vector is just 0. So it has to be a non-zero vector, and then T of W, because T of W has to be in this space, because this is invariant, it must be equal to some lambda times W. Okay. However, if you take this as a generic form and try to find out the, well, let's just quickly compute the eigenvalues for that one. So suppose T of xy is lambda times xy. But on the left side, this, I know that this is y comma 0, right? So y comma 0 is equal to lambda times xy. And that immediately says y is equal to lambda x and 0 is equal to lambda y. Now, in the case when y is 0, then x is also forced to be 0. So in the case when lambda is non-zero, then y is 0, and then x is also forced to be 0. In that case, you don't get an eigenvector. So the only way that this can have a non-zero solution, non-zero vector solution, is when lambda is equal to 0. That's what you get out of this. Okay? But if lambda is 0, if we know that this lambda is 0, look at what this says. This says T of w equals to 0. Which means w belongs to where? Null space of T, which is in U, which is equal to U, right? So that means this is not a direct sum. So it fails, okay? So that's why there does not exist an invariant subspace W, which is a disappointment. And last thing that you see is that even the quotient operator, T of, if you look at T quotient by U, let's see what happens if I do V plus U. Okay. Well, this is T of V plus U. But what is T of V? T of V is y comma 0 for some, it's y comma 0 for some y, right? Because T of any V is always y comma 0. Right? But this actually belongs to U, right? So we learned last time that the quotient map, quotient space has this equivalence relation. We say y comma 0 minus 0 comma 0. If two vectors subtract to belong to that subspace, then we say these are equivalent. They satisfy this equivalence relation so that y comma 0 plus u is same thing as 0 comma 0 plus u. Okay? And that is actually the 0 element in, this is the 0 element in u, in V quotient u. Right? And because of that, that shows that T quotient by u is also 0. Okay. So these properties tell you that when you get these nilpotent type of operators, then you cannot divide the space into smaller ones, and you just have to live with them. Okay, and that's what you're going to see again when we do the Jordan normal.